Hello, everyone. Let's start chapter 14. Okay, in chapter 14, you are going to learn about heat and heat transfer method. Okay, so in last chapter, you learn about temperature. Here, you will be learning about heat and heat transfer method. Okay, so what is heat? Okay, to understand this, let's consider a hot cup of coffee and a metal spoon at room temperature. Okay, so what happen if you put the metal spoon in the hot coffee? Okay, so here the spoon warms up, right? The spoon warms up and the coffee cools down. Okay, so that we already see when you learn about the thermal equilibrium, right? When two objects are at two different temperature are in contact with each other, uh, their temperature, at some point their temperature becomes the same. Okay, that means they are in thermal equilibrium. So the same thing happening here. Okay, so when you put the cold spoon in hot coffee, there will be thermal equilibrium between the hot coffee and the cold spoon, and at some point you will see that both the coffee and the spoon will be at the same temperature. Okay, and that is the thermal equilibrium. So you can see the same thing in this simulation. So here is the simulation. So here the hot molecules are shown by the red dot, and the cold molecules and the cold object are shown by the blue dot. Okay, so here you see in the right hand side we have a graph, and the blue dot is at 0 degrees Celsius and the red dot is at 100 degrees Celsius. That means the red object is at 100 degrees Celsius, it's a hot object, and the blue here is at 0 degrees Celsius. That means it is cold. Okay, now what happened when we bring them close to each other, okay, or in contact with each other? So okay, so you see that when you bring them together, the temperature of the hot object is decreasing and the temperature of the cold object is increasing, and at some point you will see their temperature will be the same. Okay, and that is the thermal equilibrium. So you see they are almost same. Okay, so this is the thermal equilibrium. The same thing happened when we put the spoon in the hot coffee. Okay, now what basically happening here? I mean, in terms of the physics, there is some energy in the form of heat is entering the cold object from the hot object. Okay, so heat is basically a form of energy that enters from one object to another object. Okay, when the two objects are at two different temperature are in contact with each other. Okay, so here or in the simulation, basically heat is transferring from the hot object to the cold object. Okay, so the energy is transferring from one object to the another object. Okay, now you may have the question that how heat can be an energy. So if something is energy, it can be able to do some work, right? And you can see that here in this simulation. Okay, so let's use this. Okay, now here in the pot we have water, and let's add heat in this water. Okay, and you see that you are adding heat to the water in the pot. Okay, and that is working on the turbine. Okay, so you see that heat uh, can do some work. Okay, so this tells us that this demonstrates that the heat is an energy. Okay, all right. Now, because heat is an energy, its standard international unit is joule, right? You already learned it in physics 1. Okay, but there are several other older non-standard international units are also used. Okay, one of them is calorie. Okay, and small cal is for calorie, so we use a small cal to represent calorie. Now, what is 1 calorie means? 1 calorie is the amount of heat necessary to rise the temperature of 1 gram of water by 1 degree Celsius. For example, let's say we have water, 1 gram of water at 14 degrees Celsius. Okay, if you add 1 calorie of heat to this 1 gram of water at 14 degrees Celsius, its temperature will be increased to 15 degrees Celsius. So that is the definition of 1 cal. Okay. Now you probably see the calorie in food packet, right? Or in a nutrition class if you have taken nutrition class. Okay. So that calorie, I mean the food calorie and our calorie are different, although they are connected, but they are two different things. Okay, our calories now to differentiate between our calorie, I mean calorie in physics and calorie in food packet, we use small cal for physics calorie and capital cal. Okay, for food calorie. So capital CAL means food calorie and small cal means hour calorie. Okay, and how they are related? So you see that 1 food calorie is equal to 1000 physics calorie. Okay, so remember that they are two different things. Okay, now how they're connected to the joule? 1 calorie is equal to 4.186 joule, or 1 kilocalorie is 4186 joule. Okay, it is important to know because joule is the standard international unit and calorie is just a common unit when we deal with heat. Okay, all right. The next thing is the internal energy. Okay, so internal energy, sometimes we call it also thermal energy. Internal and thermal energy are basically the same thing, and we use U to represent internal energy. Okay, so in the last chapter, you learned that the temperature is somehow proportional to the kinetic energy, average kinetic energy, right? From the when we were talking about the kinetic theory of gas, you see that the average kinetic energy is proportional to, okay, so here, so average kinetic energy was proportional to the absolute temperature. So T here is the temperature. Okay, so you see that the temperature is somehow related to the average kinetic energy. Okay, now the internal energy or the thermal energy is the sum of all the energy of all the molecules in a substance. So the temperature here, this equation tells us that it is the average kinetic energy. Okay, on the other hand, here the internal energy or the thermal energy, it is the sum of all the energy of all the molecules of a substance. Okay, so it is the total energy. On the other hand, the temperature is somehow related to the average kinetic energy. Okay, now what is the mathematical derivation for the internal energy? So it's different for different kind of molecule. Okay, for example, the simple one is the monoatomic molecule. Okay, monoatomic means one atom in one molecule. Okay, for example, helium molecule, argon molecule contains only one atom. One molecule means, I mean, one helium molecule means it contains only one helium atom. Okay, that's why it's called mono. Mono means one. Okay, so it's a simple to calculate the internal energy for monoatomic gas. Okay, for example, helium gas or argon gas. Okay, So let's say we have n moles of helium gas or any monoatomic gas, okay? And n moles, let's say in n moles, we have n number of molecules. I mean, n small n moles and capital N number of molecules, okay? So what is the energy then? What is the internal energy or the thermal energy for this? This is let's say we have n number of molecules, and then for each molecule, let's say this is the kinetic energy, okay? So I mean, let's say this is the average kinetic energy. So n molecule and average kinetic energy, when you multiply this, you get the internal energy or the thermal energy, okay? Now you know that the average kinetic energy is also equal to 3/2 kT, okay? All right, that is that you learn from the kinetic theory of gas, okay? So this tells us that for a monoatomic gas, okay, the internal energy or the thermal energy is this, okay? And this you can also write as nRT, okay? Because earlier, remember that PV was equal to nRT, or it is equal to nKT, okay? So by using that, you can either write that U equal to 3/2 nKT or 3/2 nRT, okay? Now, here this 3 has some meaning. So these 3 on the numerator has some meaning, and this 3 tells us that the monoatomic molecule can translate in 3 different directions, okay? So in space, it can go either in the x direction, or in y direction, or in g direction, okay? So in space, in our real life, there is 3 direction, okay? So 3 spatial direction, x, y, and g, right? So because of this, um, uh, I mean, monoatomic molecule, it can go in these 3 direction, and that's why we have 3 here. The meaning of the physical meaning of 3 is this, okay? Now, yeah, so monoatomic molecule, I mean, this is simple because monoatomic molecule have only translational kinetic energy, okay? That's why it's easy to derive, okay? And yeah, from the last lecture, you already know that translational kinetic energy is equal to 3/2 kT, okay? But when we have diatomic molecule, for example, nitrogen or oxygen, okay, we have to consider also rotational kinetic energy and vibrational kinetic energy, okay? So rotational kinetic energy means, you see this one here, it can rotate, okay? Diatomic means 2 atom in one molecule, so you see that it can rotate. So when we want to know what is the internal energy for diatomic molecule, we have to consider the rotational kinetic energy and also the vibrational kinetic energy. So you see that this atom and this atom can vibrate, okay? So here you see this is vibrating, this is also vibrating, okay? So we have to consider this, okay? All right, so I'm not going to derive it, but you can show by adding these 2 types of kinetic energy. The internal energy for a diatomic molecule is 5/2 nRT, okay? So I mean, physically you can show that 3/2 nRT for translational motion, and then half nRT for vibrational motion, and another half nRT for rotational motion, okay? And that's why it is 5/2 nRT, okay? So this is for translational, this is for rotational, and this is for vibrational. So for diatomic molecule, it works something like this way, okay? All right. Now for real gas, the internal energy depends mainly on T. Okay. So here you see that for monoatomic gas, it is 3/2 nRT. Okay, for diatomic gas, it is also similar, but the coefficient is different. The main thing is it depends on T. Okay. Now, when we deal with the real gas, okay, it's also true. Okay, it depends on T, unless it is it is um, it is not at high temperature, sorry, high pressure, and it is not close to the boiling point. So when they're close to the boiling point, the behavior is not, it does not depend only on T, it also depends on something else. I mean, the pressure and volume. Okay, so when it is not close to boiling point, and when the pressure is not too high, then for real gas, we can also use this equation where I mean, this for monoatomic gas and this for diatomic gas. Okay. The next thing I'm going to talk is the specific heat. Okay. Now, I mean, from our common sense, we know that when heat enters some object, the temperature of the object increases, right? Now, we are going to learn the quantitative measurement between the temperature change and heat enters. Okay. Now, experimentally, we see that the amount of heat Q required to change the temperature of a material is proportional to the mass of the material and also proportional to the change in temperature. So the heat needed to increase the temperature of some object is depends on two things. One is the mass, and another is the how much temperature you want to change. Okay. Now, if you want to combine these two equations, you can write this as this. Okay. So here you see M delta T, and because now it is an equation, equal sign, we need a proportionality constant. Here C is the proportionality constant. Okay, and it has some special name. It's called specific heat capacity or just the specific heat, and it is different for different materials. Okay, so in the table right hand side, it shows the specific heat or the specific heat capacity for many materials. Okay, in two different units. Normally we are going to use these units. This is the standard international unit. Okay, and here you see that again we are using degree Celsius. Okay, so we can use degree Celsius because the equation contains delta T, the change in temperature. So when there is change in temperature involves in an equation, no matter whether you use degree Celsius or Kelvin, it should be fine. Okay, so the same number in some textbook, it uses joule per kilogram per Kelvin, but here we use joule per kilogram per degree Celsius. Okay, and we can do that because here we have delta T in our equation. Okay, now you know that temperature can increase, temperature can decrease, right? So when temperature increase, then delta T is positive, right? So let's say you start from 20 degrees Celsius. Okay, let's say the final temperature is 50 degrees Celsius, right? Then the temperature delta, the change in temperature is 30 degrees Celsius. But sometime it could happen in the other direction. Let's say you start from 20 degrees Celsius, but the temperature decreased to 10 degrees Celsius. Okay, now you see the delta T, the final temperature minus initial temperature, is minus 10 degrees Celsius. Okay, so if temperature increase, then the temperature delta T is positive. If temperature decrease, delta T is negative. Okay, so because of that, the sign of Q can be positive and negative. Okay, so Q positive. So remember that this is the convention. Q is positive when heat enters. Okay, so when heat enters to the object, the temperature T increases. Okay, and temperature T increases means delta T is positive. And Q negative, the heat is negative means heat leaves the object, and that means its temperature decreases, and temperature decreases means delta T is negative. Okay, so Q negative means delta T is negative, and Q positive means delta T is positive. Okay, and then what is the SI unit? SI unit is joule per kilogram per Kelvin or joule per kilogram per degree Celsius. It's both same thing. Okay, again, because we have delta T in the equation, so no matter whether you use Kelvin or degree Celsius should be fine. Okay, all right. Now, the specific heat for gases are complicated, okay, than for solid and liquid. And that's why here in this table you basically see some solid object and liquid object. Okay, so the first few, these are solid, and then some liquid. Okay, but for gas it is complicated. Why? Because a gas changes strongly, gas volume changes strongly with temperature. Okay, or gas pressure changes strongly with temperature. Okay, and because of that we have two types of specific heat for gas. One is the specific heat at constant pressure, another is specific heat at constant volume. Okay, so for example, here in this table it shows two different column for two different types of specific heat. The first one is at constant pressure and the second one is at constant volume. Okay, all right. The next thing is the calorimetry. So to learn calorimetry, we need to learn some terminology. So before we learn calorimetry, let's learn the terminology and then go back to the calorimetry. Okay, so the first thing we need to understand is a system. So what is a system? The system is is an object. Basically, any object of our interest can be system. For example, a human body can be a system. A pan of water can be a system. Okay, our art can be a system. Okay, so system is basically the object of the object we are dealing with. Okay, the object of our interest. And what is the environment? Environment is the surrounding. Okay, so environment is basically where the system can release energy or from where system can get some energy. Okay, now closed system. What is closed system? Closed system means no mass can enter or leave, but energy can enter or leave. Okay, that is the closed system. Open system, mass and energy can go in and come out. Okay, so open system means it is free. So mass as well as energy can go in and come out. But the important thing is the isolated system. Okay, so we will be basically using isolated system. And isolated system means closed system where no energy in any form is transferred. That means energy as well as mass um, are not allowed to go in or come out. Okay, so the isolated system means that. Okay, and for an isolated system, energy out of one part is equal to energy into another part. Okay, that means if one part lost some heat or energy, another part gained the same amount of heat or the energy. So for an isolated system, heat lost is equal to heat gained by another part. Heat lost by one part is equal to heat gained by the another part. Okay, that means it follows the conservation of energy. Okay, so you know that heat is a form of energy, because heat lost by one part is equal to the heat gained by the other part, is basically um, representing the conservation of energy in some other form. Okay, mathematically we write something like this: sum of Q is equal to 0. Okay, and here you have to remember that Q, if Q enters into some part, that Q will be positive. If Q leaves some part, okay, that Q will be negative. Okay, so in the last slide you already learned that Q is positive when heat enters, Q is negative when heat leaves. So remember that convention. Okay, so when you write the conservation of energy, you have to follow the convention. Okay, now now we are ready to understand the calorimetry. So calorimetry is basically used to measure the specific heat of some object. Okay, and calorimeter looks something like this. Okay, it has the um, insulating part, okay, insulating jacket, and then air insulation. Okay, and that basically helps the in the and the system inside as a closed system, I mean as an isolated system. Okay, so we need this, we need the insulation to make the system inside as an isolated system. Okay, remember that isolated system means heat or mass cannot go in or come out. Okay, so that's uh, the insulating part, and then this is the calorimeter cup, where the system here is water, or let's say another sample. Okay, and thermometer is to measure the temperature, and a stirrer to stir the water for uniform distribution. Okay, now how it works. So uh, for example, you want to know what is the specific heat of an unknown sample. Okay, to know that, you have to first heat those unknown sample to a well measured high temperature, and then put it into this water in the calorimeter cup. Okay, and you know that calorimeter cup has water at, let's say, room temperature. Okay, and the sample is at high temperature. So when they are in contact, okay, one object lose heat. Okay, that means the sample will lose heat, and the water will gain heat. Okay, and then by using the conservation of energy equation, you can determine the specific heat of the sample. Okay, we'll be learning, I mean we'll be doing some example problem how to do that. Then it will be more clear how we can measure the specific heat by using the calorimeter. Okay, now another type of calorimeter is the bomb calorimeter. Bomb calorimeter is used to determine the calorie content of the food. The technique is little bit different, but the physics is the same. Okay, so one part, the physics is one part of the object inside the calorimeter will lose heat, and another part will gain heat. Okay, and then by using this physics concept, we can determine the content, the calorie content of the food. Okay, using the bomb calorimeter. Okay, so the important thing in the calorimeter for all kind of calorimeter is that calorimeter must be well insulated. Okay, so that means the system should be isolated. Okay, if the system is not isolated, energy or mass can go inside, um, go into the system, or come out of the system. Okay, so make sure when you I mean if you deal with calorimeter in real life, we have to make sure that it is a isolated system, and isolated system means it should be well insulated. Okay, so for example, here in this picture you see that it is insulated first using the air and then insulating jacket. Okay, so I'm going to stop it here. In the next class we will be learning about latent heat and three different methods of heat transfer.